Well, we are going to get started just a little bit early today because we have a very full schedule. There's a few seats like in the back and stuff. So I'm the Modesto Junior College MESA director, and I have the honor to present today's science colloquium. Today's presenters are 5 groups of MESA students who have been working all semester. Research projects related to the circular bioeconomy.
We're just going to leave it like this, and then sounds good.
Okay, well, I'm going to speak loudly. We'll get another battery here. So before we get started, I wanted to give you guys a little bit of background on what, because all of our speakers are going to be talking about what the circular bioeconomy is. So I want to give you guys, or all of the topics are related to this. So I want to give you guys a little bit of background about what the circular bioeconomy is and why it's important for our region. So basically, the circular bioeconomy has to do with the use of biological resources and especially biological waste to produce food, materials, and energy while keeping resources in use for as long as possible through recycling, reuse, and regeneration. So this could be something like using almond hulls to create bioplastic, which then gets recycled and turned into another bioplastic. So keeping things as part of the cycle and the second use and third use of items. And why this is important in our region is especially well situated to be a leader in this industry because we're a global leader in large-scale agricultural production and food processing already. This means that we have both extensive manufacturing infrastructure and large amounts of biological waste inputs as secondary products. So, like I said, things like almond hulls or manure, even municipal waste. And then our region's proximity to the San Francisco Bay Area and regional centers of technology also gives us access to world-class biotech and ag-tech innovation. Finally, we're a region in need of improved environmental and social conditions, including better air quality, better water quality, and more high-quality jobs and community wealth. So we're a region that would really benefit from this new industry. So we do hope that as our students have done this research, that these projects will have inspired them to continue this work in their future endeavors, and that some of them will go on to be leaders in this new industry. So there's our group there. This work would not have been possible without the financial backing and support of Being Circular, who is a key player in building this new industry for our region. I would also like to thank our faculty mentors. If you want to raise your hands in here. Yay, thank you for being here. Noah Hughes, Andrew Lazar, Daniel Hicks, Wendy Chen, Parker Wright, as well as our library support team, Kathleen Innes, Sarah Cottinger, and Ian Miller. I know how much you guys are already have a lot on your plate, so thank you so much for believing in this project and taking the time to help all of your students. So we are squeezing in 5 student groups today during these presentations, so there won't be time for questions between the presentations, but please do stick around after the event to visit student posters, ask any questions that you have. We'll be sticking around. So without further ado, I'd like to present our first group, and this is going to be just speak loudly, and we'll get the microphone.
Applications of microbial for biodegradation of non-nutrient.
This is really hard on it.
We'll be
front.
break down waste
There's like
is for
my
a more
teaching is
sustainable
there.
and a cleaner world. We'll be looking at modern waste forms and issues, microbial consortia and biodegradation basics, case studies, and Central Valley and global implications. Before I talk about microbes, I wanted to point the types of waste we face as of today. Some examples are petroleum-based oils, consumer industrial plastics, organic waste such as food scraps, agricultural runoff from farms, industrial byproducts like metals, heavy metals, oils, and other toxic substances. And in our research, we focus primarily on oils, plastics, and organic waste. Our current waste system is very large. It's very expensive. It's very unsustainable to handle due to the increasing demand in waste management. And some of the methods that we use, first being the relocation, moving waste from one place to another, storing the waste and burning the waste, which increases the gas production and the greenhouse gases. And due to the increase in waste production, it leads to less land to manage the waste. And these methods are very expensive and they're very polluting. And this needs to be for alternatives, which is why the microbial consortia is a very promising. Microbial consortia. Microbial consortia are essentially microorganisms such as bacteria, fungi, yeast, algae, and archaea, etc. that they work together, interact with each other, and the existing microbiomes. They're important because they're very adaptable, they're very efficient, and they're organic, they're natural, and they're ecologically symbiotic. They can be used to break down tough materials using their enzymes. They produce and engineer, enhance each other's metabolism, and turn waste into useful resources, which is called valorization.
So for microbes to be able to degrade waste, first they're going to need to be able to colonize the waste, so grow in numbers and be able to reach the waste molecules. Next, microbes need to be able to metabolize the waste through their enzymes, and they do that by attacking or grabbing functional groups of waste molecules to modify. This is the most difficult step because a lot of synthetic waste like plastic and oils don't always have functional groups to attach onto. After that, waste is kind of degraded through a bunch of metabolic processes, and they can become metabolic byproducts, water molecules, CO2, and some other forms of waste that will be turned into valuable resources like fertilizer. So functional groups, they are certain groups that are added as part of the molecule that gives it its properties. Some examples are hydroxyl groups, the oxygen hydrogen, carbonyl groups, carbon, and ester groups. So you guys can make a little bit the carbon into oxygen. So when a functional group is present, certain enzymes that microbes produce are able to actively break that molecule down, and those products are used in other metabolic processes that the microbe has. If there's no functional group present, there's nothing for the enzyme to act upon, and the molecule is intact. So an example of the degradation process, first we have a unit of PCl. So PCl plastic are long chain of these units. You see that there's an ester group right there. A microbe produces enzymes, in this case the relevant enzymes are esterases. That with water is able to act upon the ester group of PCl, produce those other functional groups, and behind short hydrocarbon chain produces other metabolic processes, which makes PCl plastic biodegradable. On the other hand, we have this polystyrene unit. So our microbes still produce enzymes, but it's unable to act on this polystyrene molecule because this has no functional groups. It has a very tight degradation. To degrade plastic, microbes must use enzymes that are able to cut up the long chains of those units, which is called polymerization. Next, if there is no reactive function present on the plastic, which is often the case, it needs to be able to oxidize those plastic molecules and then metabolize those molecules. So this study looked at these microbes that produce these 7 enzymes. 4 consortia, all with the subtilus strains, mixed with various bacteria and fungal strains. We tested 4 of the most prevalent kinds of plastic waste we have, polystyrene, and then 3 polyethylene plastics, PET, linear low-density polyethylene. The results of this were that polystyrene cannot really integrate for the reasons we just spoke about. The polyethylene plastics, recycled PET was able to be degraded, have 6% weight loss in 30 days. Linear low-density polyethylene had anywhere from 15 to 17% weight loss. Recycled low-density polyethylene had about 11 to 18% of its weight loss. We see some contrast between the virgin and recycled forms, and we'll look at why that is right now. So PET plastic, it has 2 of these ester groups that we saw earlier on each side of a benzene ring. So ester groups are present, enzymes are able to attack those groups. The presence of that ring hinders the ability of those enzymes to fully latch onto this PET unit. The chains of PET are also very tightly packed together, which blocks the ability of enzymes to really be able to attach to them well, and that makes its degradation not impossible, but very slow and difficult, which we saw with the 6% weight loss results. Next, this is a unit of polyethylene. Those 2 low-density polyethylenes, these are each how they look, so linear low-density polyethylene and low-density polyethylene. They all branch off and have these long chains, so they are amorphous. Low-density chains means they're not very tightly packed together, relatively, so that results in low crystallinity. The places where the branch is split and the ends of those chains are able to be oxidized pretty easily, which results in enzymes being able to metabolize them. But as we saw from the results before, recycling is a double-edged sword. It can either make these molecules more accessible for enzymes to attack, or they can make them too smooth for enzymes to really do much about. A molecularly similar kind of thing is oil waste. So in this study, they took some samples around a petroleum plant of soil, and they used these 2 strains, Bacillus subtilis, the wild bacterial strain, and Starmarella bombicola, a yeast strain, and with supplementary swine wastewater and wheat bran, it was able to reach 68% oil degradation in only 40 days in those soils. This is in contrast to the native microbes, the ones that already existed in the soil, only having 5% oil degradation in 40 days. So the chemistry behind that, oil has very accessible hydrocarbons. They have flexible backbones. That makes them easily oxidizable, which makes them metabolizable, which then, with the right enzymes and microbes, makes it biodegradable. Lastly, organic waste, which is the type of waste that is the largest fraction that we have to deal with. It's naturally highly biodegradable. It has already very natural, very common biological functional groups. The study used consortia that are high in lipase, pectinase, cellulase, and protease production, all very common enzymes. The results were that they were able to take the heaviest was a 30 kilogram sample of organic waste, reduce its volume by 80% in 30 days, reduce its mass by 65%, its moisture content by 65%, and doubled its density from about 0.45 to 0.9 grams per centimeter cubed. These were the visual results of the waste. Its sulfur, potassium, and phosphorus content all increased slightly. It became less acidic, which is pretty useful in an era of increasing soil or decreasing amounts of usable soils. The 30 kilogram sample became very dark, very grainy. It did not have any kinds of crustaceans or insects in it, and it was odorless, which is a big quality of life issue in the Central Valley, very smelly organic waste. Like I just mentioned with its role as a fertilizer, it is able to also be a possible solution to the increasing soil vulnerability we face as a result of desertification, climate change, etc. Implications for the Central Valley.
From UN statistics, urban growth is projected to increase by 2050, and 89% of Americans will be living in urban areas, which is why we must ensure the sustainability, urban expansion and agricultural development. Microbial consortia research supports soil and public health, energy production, pollutant degradation, and quality of life in the Central Valley, and provides possible solutions to our greatest agricultural and economic challenges. And now we want to thank our MESA director, Ilana Peach-Fine, and our faculty mentor, Danielle Hicks, our library research team, and Beam Circular. Thank you.
And my name is Gisleni, and our presentation is on the literature we conducted on machine learning and predictive modeling of bio-based organic. And a brief overview of what we will go over. We will start with a brief background, then we will delve into our 3 case studies, and finally end with our conclusion. So in California, we have a lot of potential for waste valorization, particularly because we produce a lot of agricultural residues, food waste, cow manure, woody biomass, and sewage sludge. And essentially, instead of sending these off to landfills or incineration, we could be using them as raw resources to create valuable and renewable products. So, however, the processes that convert waste into products are highly complex, and the specific combinations of temperature, pressure, pH, and other variables can drastically affect the resulting product. So traditionally, these processes are optimized through trial and error, where researchers will gradually change the variables in order to reach the optimal conditions. However, this takes dozens to hundreds of experiments, and it can be really time-consuming and also resource-intensive. So, however, if you use machine learning, we can optimize these processes through minimal lab work, and this is because the models are trained off of existing data from published studies and also various databases. And once they are trained, they can predict not only the optimal conditions for these processes, but also the characteristics of the resulting product. So why use machine learning over traditional programming? Well, traditional programming requires hard-coded rules, which fail to take into account correlations between the data that we are unaware exist. Whereas machine learning can learn these patterns directly from the data, and it does account for unknown correlations. It also does not require simulating the entire complex chemical reactions that occur in the reactor, and it improves over time as they learn some more data.
And so for the types of machine learning is a very broad field. And our project mostly focuses on supervised learning, and so this is giving the model the labeled input and output, and from there, any other input that is given is able to predict it on its own. And then for unsupervised learning, we would give the model the unlabeled data, and it would find its hidden patterns and structures on its own. And then for pure reinforcement learning, it's going to be learning through trial and error. So for the process of creating a machine learning model, so at the start we collect the data, whether it be from our lab results and from published studies. And then the next part of creating the model is processing the data. So if there's any errors in the columns, any missing items, we would clean up the data and have it ready for inputs. And so we would be inputting it into our machine learning model here. We would select the algorithm, and then from there we would now split our data into 80-20 after selecting the algorithm. 80% of that would be spent on training the model, and so it would learn the patterns and structure of the data, and from there we're going to use that output, any outputs from that model, and compare it to the 20% of the data. And so evaluating that model accuracy, we would select from the best two, or however many models we're comparing against. And so we compare that with our R-squared and our MSE. And so our R-squared is going to be our accuracy score from 0 to 1. That's going to be showing how the model's prediction matched the real world data. So we're going to see here, this shows little to no correlation with the small R-squared, and then this is going to be good correlation with the high R-squared. And then for our root mean square error, it's going to be a penalty score that measures the average size of the model's errors in the same units as the products.
So onto our first case study, we will see how machine learning was used to optimize the production of hydrochar produced from municipal solid waste via hydrothermal treatment. And on the left, you can see that these are the three specific elements that the study focused on. They focused on food waste, cow manure, and sewage sludge. And the process that they used to turn this into hydrochar was hydrothermal carbonization. And hydrochar is essentially a solid fuel used for heat and is also a soil amendment and an absorbent for water purification. So this was the process that they selected. They chose this one specifically because it works well with wet waste. And it essentially treats the waste with hot pressurized water, and it breaks it down into our hydrochar. So they selected a total of 2 models to compare. They selected the assembled vector machine and the random forest. And they collected a total of 306 data samples collected from existing filter studies. They then separated 90% of this data to be used to train the models, and the remaining 10% was used to test the accuracy of models. And specifically, this data consisted of characteristics of the waste, the conditions that the waste is treated with, and also the resulting properties of the hydrogen. Now, for the results, they found that of the two, the assembled vector machine was the more accurate model, with an average R-squared of 0.94 and an average root mean square error of 2.62. And for our R-squared, the ideal R-squared would be closest to 1, whereas the RMSE should be as low as possible. Now, these were the predictions that the winning model was able to come up with. Here is the ideal temperature, time, and water content to produce hydrochar for the purpose of using it as a fuel, whereas these were the characteristics that they predicted the hydrochar would have when produced under these conditions. On the other side, these are the ideal conditions to produce hydrochar to be used as a soil amendment, as they maximize the carbon capture stability. Whereas down below are the specific characteristics they predict with this hydrochar would have.
And then on to case study 2, biochar produced from cattle manure via pyrolysis. And so cattle manure is a big waste that we have here in the Central Valley. And this study aims to show how it can be used to produce biochar. And so what is pyrolysis? So this is a process where you heat organic waste, like the cattle manure from our case study, to high temperatures. And the key part is that this is going to happen in the absence of oxygen, because with oxygen, the waste then burns. And so without oxygen, this is going to chemically decompose into valuable products. And it's also a fast alternative to composting, taking hours, not days or months, and this avoids methane emissions and drastically reduces waste volume. So in this study, they tested the 2 models, the artificial neural network and the least square support vector machine. They ran 33 lab experiments, 70% of that training the model, and then testing the 30%. And then these are the 5 inputs that they put in, and then with the goal of seeing the biochar yield. And so for the results, we saw that in the training of the model, the ANN scored the highest R-squared with a 0.995, and we see that it drops in the test R-squared with a 0.804, showing a classic problem of overfitting, whereas compared with the support vector machine, we saw that the R squared for the training got a 0.915 and increased in the test and outperformed with a 0.963.
Now, on to our last case study, we saw how machine learning was used to optimize the production of biolubricant from waste cooking oil and sewage sludge via transformation. So for this study, they selected sewage sludge and waste cooking oil, particularly because of their high lipid content, making them ideal for transformation. And they produced biolubricant, which exhibits not only higher wear resistance compared to regular commercial lubricants, but it is also biodegradable. And for the waste-to-product process used, they began with a lipid extraction, where they used texting solvent to extract the lipids from the sewage sludge. Then they combined these liquids with the waste cooking oil. For step 2, they performed esterification, where they converted the free fatty acids into esters. And the reason they did this was because otherwise the free fatty acids would form waste in the transformation, soap in the transformation process. And for step 3, they performed transformation, where they used the triglycerides from the waste and added methanol, ethylene glycol, and potassium hydroxide to create methyl esters and glycol esters, which are essentially our biolubricants. And this is the step where they use machine learning to optimize these conditions.
And so, on to the model results. So we saw this was a hybrid model with artificial neural network, and then the ACO, the ant colony optimization. So to break it down, essentially, the ANN is sort of the brain of the model, and then the ant colony optimization algorithm was inspired by ants on how they find the shortest path to food, and it would input the optimized inputs or the dials that we have here, such as the reaction time, and feed that into the ANN. And so we saw that the accuracy model with this hybrid model was a 0.977, and this was validated through an experiment where the model predicted yield was 96.88, and the actual lab yield was 96.14, which was a very successful experiment. And we also saw that the biolubricant that was made from the study was better than commercial lubricant products with 23% less friction and 44.4% less wear on metal parts. And it also met industry standards. And so in conclusion, we see that machine learning wasn't just a theory, but it's a practical and proven tool for waste valorization. If we go over to the graphic, we can also see that organic waste makes up 28.3% of the waste that we have here in California. So changing this waste into valuable products really makes an impact. And then so looking forward, our plan is to build these custom models within the Central Valley using local feedstock and building our own model, and then putting that into smart refineries that use real-time sensors to adjust temperature and pressure, and then to get the highest yield, and having that run 24/7, changing our waste stream into a value stream. And then so we also wanted to give a special thanks to our professor Chen, our mentor for this project, and Beam Circular for funding this project, and MESA for giving us this opportunity. Thank you.
Hello everyone. Wow, we have a full house tonight. Thank you all for coming today. My name is Berenice Vasquez, and this is my partner, Janessa Cervantes. And today we'll be, And today we will be presenting our literature review on the optimization of waste to product in the supply chain. And you might be wondering, what is a supply chain? The supply chain is the entire process of getting a product from the very beginning all the way to the consumer, as illustrated on the screen. And our goal here is to stop relying on raw goods and use and optimize our biological waste that we have already created. while reducing, while balancing cost, emissions, and resource recovery. But what are some examples of waste to product?
Okay, so what are some examples of waste to product? In our literature review, we're focusing on optimizing agricultural waste. And one way agricultural waste can be transformed is into biomass. Biomass is a form of stored chemical energy derived from the sun during photosynthesis. And our job is to repurpose that energy to create a sustainable and circulatory system that adds valorization back to items that would have just been labeled as waste. So some ways that biomass is derived is through crop residues and food processing byproducts. And some ways it can be converted is into bioethanol and biochar, among many other things. So as you can see, I have a diagram of how bioethanol specifically is transformed or converted. And the purpose of having this illustration here is to kind of show you guys a small portion of the supply chain that we are going to be examining here shortly.
Alright, so the mathematical technique that we found in our studies is called mixed integer linear programming. First, I'm going to break down what mixed integers and linear programming are. So mixed integers are both our rational numbers and our integers, and we use them when we are picking our decision variables, such as x, y, and z. And linear programming is what helps us find the best solution within all of our constraints. And our constraints, such as supply limit or capacity limit, and once we combine both mixed integer and linear programming, we get mixed integer linear programming, which we'll be calling MILP for short. And this allows us to use both rational numbers and integers while optimizing a specific function. And in this presentation, we will be looking at how these studies applied MILP in their models. Alright, so now that we understand what MILP is, we are able to see it visually. So our parameters are going to be constants that do not change. And for example, that would be our storage and distance. And we organize all of that into sets, such as B for biomass and I for harvest sites. And our variables are going to be what we solve throughout the system, and that is going to be in the shaded region. And we are solving for the optimal point. So as you can see, we also have a blue arrow pointing up. So for this graph, we are trying to maximize an objective. If the arrow were to be pointing down, that would mean we are trying to minimize an objective. And now that we understand how MILP works and we have a visual of it, we can understand the math behind it.
Yeah, so now that we have an understanding of what MILP does, we're going to be going over the simplest version of looking at the equations in the articles. And then we're also going to be going over a general equation that I coded in order for us to dissect the equations from articles that utilize MILP. So in its simplest form, as you can see, I have z is equal to c dotted with x transpose. And what the z is going to represent is our objective. So if we want to minimize or maximize something, we have to dot the coefficient with the decision variable. So an example of this happening is, say, if you wanted to find the minimum cost of operating a facility, you would have to dot the cost of that activity with if the facility is open or closed. So now applying that thought to a more complex mathematical model like MILP, we're going to be utilizing a summation that condenses multiple coefficients and multiple decision variables. And as you can see on the coefficient variable and decision variable, they have subscripts. And as you can see, those subscripts kind of tell you what part of the supply chain these variables are assigned to. And then on the summation, we have a lower limit and an upper limit. So our lower limit is going to be I is equal to 1, which lets you know our starting point, and that we have at least one of anything that we are considering. And then we have our upper limit denoted by n. So say if we had 5 warehouses, we would have a 5 in the place of that n. So now moving on to our matrices. As you can see, I have a row vector of coefficient variables, and I have a column vector of decision variables. And so leaving these just as is isn't going to give us a single number. So we have to multiply these vectors out to get a single number. And the reason we can actually multiply them out and perform dot product is because they're flattened out. So the columns of the first matrix are equal to the rows of the second. And as you can see here, that you're going to multiply the first coefficient by the first decision variable, and this is going to continue all the way to the nth variable. And then once you perform all these products, you add them together to get our single number. So now we're going to be going over our first case study, which was conducted in Mexico, and they used corn and barley residues to minimize a bioethanol supply chain. Okay, so as you can see here, in this study they utilized single summations, but we will also be looking at multiple summations. And these summations represent how many dimensions we will be adding costs across. So moving on to the single summation, there's only one dimension we are considering because here you see J is denoted by warehouses. And to get our our total annual cost of the distribution centers, we would have to multiply that cost coefficient, which is the annual cost of construction, amortization, and operation of the warehouse. And you'd have to multiply it by this binary variable. And this binary variable is going to let you know if the warehouse is open or closed. So if it's open, the product will be added to our summation, but if it's closed, it will zero out and it won't be a part of our summation. Okay, so now we have two dimensions, and we will consider T for time periods and K for biorefineries. And to get our total cost for storing bioethanol in the biorefinery, or bioethanol in the biorefineries over selected time periods, we will multiply the cost of holding bioethanol by the amount of bioethanol stored in the biorefinery. And then now this triple series performs a sum over three different indices, which are our harvest sites I, our biomass types B, and our time periods T. So every combination of these three things will contribute to the overall cost, and the summation will result in the cost of holding biomass at a harvest site. And now for this quadruple series, it has 4 dimensions to consider for finding the total cost of transporting biomass from the harvest site to the biorefineries. To find a single number, we will have to multiply the cost of transporting the biomass from the harvest site to the biorefinery by the amount of biomass that's being sent over all 4 of these sets. Okay, so now we're looking at our objective function that sought to minimize the overall cost of the bioethanol supply chain. And as you can see, they utilize the same summations that we just broke down and other summations that follow suit to according whether they are single or multiple summations. And these summations are meant to perform dot product over a cost and a decision variable, and they'll all result in single numbers to be added together, and we're supposed to get one number for our minimum cost. So now Bernice will be going over 2 studies conducted utilizing them.
Thank you, Janessa. All right. Ooh. Okay. Sorry about that. All right. So in this case study was conducted in Belgium, and the authors used a slightly different model. It's called Optimass, but it works and functions the same exact way as milk. And their objective was to maximize electricity output while designing a biomass system that works effectively, as we have illustrated on the screen. And then in our third case study, this one was pretty cool because they actually generated their own data, and they were just testing out how milk works under different scenarios, and their main objective was to see how can milk maximize profit. And now to our conclusion. So in conclusion, we found that even though all 3 of these articles have 3 completely different objectives, they still all use the same model, which is milk. So this shows how flexible milk is and how it supports our biocircular economy. And now Janessa will be going over some overall benefits.
Okay, so according to an article that was actually conducted here in the Central Valley, it was found that biochar can maximize resource recovery and reduce emissions. And I was thinking by utilizing these findings, we can link these results to other biomass systems to further enhance job growth and economic prosperity within Californian communities. So milk would help us identify optimal location, how much material should flow through each location, and plan most efficient routes. And for a region like the San Joaquin Valley, where we're highly impacted by unemployment rates, and we have a lot of communities that rely on agriculture, MILP would help guide up investment towards places that can benefit most. And MILP would help us map out where these new jobs can be created while keeping costs affordable. So we'd like to give a special thanks to Being Circular, our MESA director, Ilana Peachfine, and our mentor, Andrew Lazar, for making this internship experience possible and supporting us through this journey.
Hello everyone, my name is Alondra Robles. Give us a quick card. Today we're going to be talking about the catalytic conversion of agricultural waste into biofuels. So let's start by defining pyrolysis. Pyrolysis is a process of thermal decomposition of organic waste into smaller components with the absence of oxygen. So this is usually conducted with biomass at 500 degrees Celsius or above. Here we can see that for pyrolysis to take place, it either needs to go through a pre-treatment or it needs to go through upgrading after to get our desired product. So we're going to be focusing specifically on catalytic pyrolysis, which is done in fewer steps. So what is catalysis? Catalysis is the acceleration of a chemical reaction through a substance called a catalyst. So what the catalyst does, it opens up different pathways in our reaction, essentially speeding it up. So here we can see that with the catalyst present, it takes less energy for the reaction to occur versus without a catalyst. Oh, it's also important to note that the catalyst doesn't get consumed with the reaction. So 3 parameters that we can use to determine how effective the catalyst is. Activity refers to the rate at which the reaction proceeds. Selectivity is how well it can produce them without byproducts. And stability is how well it can hold these 2 qualities over time. So zeolites. Zeolites are a type of catalyst that we're going to be focusing on throughout our studies. They're composed of silicon, oxygen, and aluminum molecules. So their catalytic properties are tunable, which means we're able to adjust them to fit whatever reaction we need to take place. So there are about 250 frameworks of zeolites so far. They're relatively new, and here are some of them. So it's important to note their porous structure, which you can kind of see here, which we're going to highlight later in our studies.
Now the main question is, what do we want from catalysis? All we want to do is move from these complex looking structures to those simple ones via catalyst while also making sure that it's a higher yield and better quality. So these complex looking structures right here are the components that are found in biomass. It includes cellulose, hemicellulose, and lignin, while on the other side, those simple looking structures are called biofuels, which include bioethanol, biodiesel, and syngas, which can be converted into biofuel using a specific method. So in order to see which catalyst gives us the highest yield and better quality, we looked at 3 different kind of studies. So the first study was called Upgrading Mixed Agricultural Plastic and Lignocellulosic Waste to Liquid Fuels by Catalytic Pyrolysis. In this study, the researchers collected the agricultural mixed waste from the farms in northern Idaho. This agricultural mixed waste had 2 major components. The first was plastic, the second one was biomass. The catalyst that they used for the study was called zeolite Y, and it had a really high surface area. They also used the regular gasoline as a standard reference. Onto this next step of the study, they did the feedstock preparation, which basically means that they cleaned the agricultural mixed waste, mixed it, and homogenized it in a twin screw extruder, and here's how it looks like. Oh my god. They also looked at the characterization of the waste, which includes the composition of the carbon, hydrogen, nitrogen, ash, and moisture content. They also did the biomass analysis, looking at the composition of lignin, cellulose, and extractives. For the plastic analysis, they used the DSC and DTA, which are two different methods to study melting and thermal behavior of the plastic. The purpose of doing all of this was to make sure that the feedstock that was going into the pyrolysis was well known and it was well consistent. And here's the whole setup of the experiment they did. They had two batches of waste, which was called CMP and BMP. Both of those batches underwent thermal pyrolysis and catalytic pyrolysis. And the process of pyrolysis took place in that batch tube reactor. Once the process was done, the bio-oil, which was a liquid product, was collected in a U-tube condenser. The gas products were collected in a gas chamber, and the solid char was collected as well. After that, they did the product analysis using all those different methods listed up there. Now onto the results. So they found out that the thermal pyrolysis at 500 degrees Celsius produces the highest yield of 70% for BMP and 73% for CMP. Whereas for the catalytic pyrolysis at 600 degrees Celsius, it was way less, like 50% for BMP and 46% for CMP. But the highest yield doesn't always mean a better quality. So which means that for the catalytic pyrolysis, even though the yield is less, it's of better quality because it's less oxygenated and has a higher heating value. Also, the formation of lighter hydrocarbons during catalytic pyrolysis indicates that the structure was more similar to the regular gasoline that they use as a standard reference. Now on to the second study.
Okay, moving on to study 2, thermochemical conversion of anaerobic digestate into light transportation biofuel over the HZSF-5 catalyst. So this is one of the zeolites we identified earlier. So in this study, we took anaerobic digestate and we synthesized that into biofuel through catalytic pyrolysis and then thermopyrolysis. And it compared the quality of the two. So anaerobic digestate is a byproduct of anaerobic digestion, which takes the absence of oxygen and breaks down organic waste through microbial processes. So here is the composition of our anaerobic digestate, and even though it goes through a different process beforehand, it's important to note that it's still agricultural waste. Okay, so we're going to look at our biofuel quality now, and we're comparing our non-catalytic process with our catalytic process. So overall, we're just looking for structures that are most similar to fuels we already use, like gasoline. So better deoxygenation equals better fuel. So we had lower levels of oxygen throughout our catalytic processes, which indicates better, more stable fuel-like product. So our oxygenated and nitrogenous compounds were reduced up to 75% with our catalyst present. Our high heating value was also improved using the catalyst, and we got biochar-rich nutrients suitable for soil amendment. So although like our aromatics here being higher isn't ideal with our catalyst, it was balanced out by our quality here. These two groups being higher indicated a less tar-like product, and these groups with the catalyst being lower indicated a better biofuel quality.
On to the study number 3, which was titled Catalytic Pyrolysis of Corn Stalk for the Production of Aromatics, the Effects of Wet Torrefaction and Zinc Nickel at CSM5 on Pyrolysis Behavior. For this study, the researchers collected corn stalk as agricultural waste. They had 2 batches of those. The first one was just regular corn stalk, and the second one was wet torrefied corn stalk, which basically means that they pre-treated it to remove oxygen content. For the catalyst that they used for this study was HCSM5, zinc HCSM5, and nickel HCSM5. For the feedstock preparation, for the first batch of corn stalk, they dried it and down-steeped it. For the second batch of the corn stalk, they did the wet torrefaction at 220 degrees Celsius. They also made some catalysts, and they prepared them by impregnating zinc or nickel onto the HCSM5. They also did the composition analysis, and for that you can see the table right here. The materials were CS, which stands for corn stalk, and CSWT, which means the corn stalk wet torrefied. The oxygen content of corn stalk was about 50%, but it dropped down to almost like 40% when it was like wet torrefied to remove oxygen content. For the pyrolysis setup, they did the fast pyrolysis in a quartz tube reactor. The temperature of this whole setup was about 550 degrees Celsius. The nitrogen was used as a carrier gas, and the biomass to catalyst ratio was about 1:3. Once the process was done, they collected the products. The vapors that were formed during this process was condensed into liquid bio oil. The gas was collected, which was analyzed by GC, which means the gas chromatography, and then the solid char was collected as well. Now onto the results. As you can see for both paragraph A and B, the CS and CSWT, both of them has a lower mass fraction of bio oil, but as soon as you put the catalyst in it, it shoots up really fast. So the major takeaway from this study was that the catalyst plus wet torrefaction equals the best combo for having a bio oil, which is like of higher yield and better quality.
So let's take a look at our different catalysts and their costs. So up here, these top 3 catalysts, you might recognize them from your chemistry class. They're more commonly used as catalysts, but it's also important to note that they're more expensive versus these down here. These 2 are zeolites, and they're a lot cheaper. So cost is mainly the only metric we have to compare these things. We want to be able to compare them through our selectivity, activity, and stability that we defined earlier, but in order to do this, we need to have more standardized studies of them. So more experiments need to be conducted in the real world. And that includes standardizing catalyst load, the concentration, the temperature, the pressure, and the flow during the actual operation. So our goal with this literature review is the growth and development of a circular bioeconomy in our Central Valley. So to move forward, we must expand the studies being done and bring this to the real world, as well as the collaborations between scientists, engineers, growers, and industry partners. So we just want to develop and optimize solutions tailored to our region specifically, whether that means resource cycling, the almond holes that you see while you're driving down the road, and our tomato pumice and our rice straw effectively. So with that, we want to give a special thank you to Beam Circular for funding our project, our amazing MESA director, Alana Peach-Fine, our mentor, Dr. Arthur White, for guiding our research. We're just really grateful to be able to do this product, and to all of you for showing up.
Hi, my name is Santiago Sasiki, and I will be presenting When AI Goes Green, Revolutionizing Life Cycle Assessments for the Circular Bioeconomy. I will also be presenting on behalf of my partner, who unfortunately was not able to be here. So the purpose of our research is to see how AI could help facilitate life cycle assessments. And AI would simply be used as a tool to help with the overall tediousness and cost of the LCA. What is a life cycle assessment? Essentially, a life cycle assessment is a tool that looks into a product's effect on the environment from start to finish. On the diagram on the right, that would include the raw material extraction, manufacturing, assembly, as well as transportation and distribution, while that product is being used, and the disposal or recycling. The results from the LCA would also help with grading certain practices from companies, policymakers, and consumers. They also do help with the circular bioeconomy because they're showing the level of impact that certain products are having, and it helps overall optimize systems. But they do come with a large issue, and that is the large amounts of data needed, and that goes through the steps that actually go into making the life cycle assessment. So the first step would be to determine what is going to be included and not included in the study. Secondly would be the life cycle inventory analysis, where we're analyzing the different inputs that are going into the study. And this is essentially the main data collection of the assessment, where the practitioner will have to take data directly from where that product is being used and being made. The third step would be the life cycle impact analysis, where we're looking at from different mediums how this product is affecting from the different outputs that are going into it. And lastly would be the interpretation phase, where we would look at the information once again and see if we would use this product or if it's more favorable to another that is showing lesser or more impacts in certain areas. So in a way that AI would help alleviate some of this would be the large amounts of data that is being processed. It would simply
gather the data, analyze it, look at the patterns, and help lessen the time that is needed to conduct LCA because there's so much data. So how did LCA start? Well, first LCA started with Coca-Cola in 1969, where they did a study on beverage bottle selection, but it did not gain much traction until the 1980s. And in 1990, it was proposed by the Society of Environmental Toxicology and Chemistry, but it was not fully established and integrated into the ISO 1400 Environmental Management Standard in 1993. Three findings that I will be going over, two of them fall under the agricultural area, as well as one in industrial. So for the first study, we'll be covering cumin and funnel. So in this study, it was conducted in Iran. They collected data from 40 different cumin farms and 50 funnel farms, and they looked at two different AI models, being artificial neural networks and adaptive neural fuzzy inference system, and compared the two to see how accurate they could be in conducting an AI-enhanced LCA. And here off the chart to the right would show the results of a set LCA, showing three different impact categories: human health, ecosystem, resources for both crops, and each of those are split in terms of their contributors, being direct emissions, machinery, nitrogen, phosphate, potassium, and so on. These models also showed high R-squared values for the accuracy for cumin, and then achieved 0.85 R-squared, while adaptive neural fuzzy inference system achieved an R-squared of 0.93, followed by 0.95 and 0.96 for both cumin and funnel. Our next study was covering soybean, and specifically how the impact of soybean cultivation under different crop rotation scenarios would be done through, once again, two similar AI models, artificial neural networks once again, and another variant of adaptive neural fuzzy inference system. So here they once again collected data from soybean farms and interviewed farmers from those areas. And both AI models did show instances of being able to analyze the data and make certain inputs, because there are certain regional data gaps whenever the data is collected.
Awesome.
Here we have a chart for the mean average percent error for both AI models. Clearly we have the adaptive neural fuzzy inference system outperforming artificial neural networks in all four categories, being human health, ecosystem quality, climate change, and resource, as well as another graph for R-squared to show you the accuracy. We have the adaptive ANFIS AI model outperforming. Lastly, for geothermal concrete, this study was conducted in India, and the goal was to improve the overall sustainability of geothermal concrete, which is already a better alternative to Portland cement. And here they once again compared three different AI models, compared to the two from earlier, to traditional LCA methodologies. And the results did show that AI was able to have a much higher accuracy when conducting these LCAs compared to traditional LCA methods. And here in the first pie chart, we have reduction in carbon emissions using AI for geothermal concrete, and we have a 12.5% reduction for traditional LCAs, while three other models having double, if not more, of that reduction. And over to the right, we have a performance comparison of the AI models to the traditional LCA methods in terms of accuracy, scalability, and speed. And we can see that the AI models are hovering over or around 70 to 80% accuracy, while the traditional LCA methods are around 50%. It is much easier to scale these AI models because they've already been trained to handle these data, so if more is added, they're already used to it. And because it is the AI and not, let's say, a person analyzing the information, the overall speed of the lifecycle assessment is increased. So why is this important? Well, the whole purpose of research was to, for the sake of San Joaquin Valley, further improving lifecycle assessments would help with the circular bioeconomy, because they are already telling us how much a product is affecting our environment, and by further optimizing that, we're just optimizing everything in general. The studies also showed improvements in energy use, fertilizer inputs, and emissions. But across all of them and other meta-analysis there are common limitations, such as regional data gaps for when the studies were conducted. They're going to be much different than if they were conducted here, because we have different methods. We are transporting our crops or different products differently. We are manufacturing some products differently. There is also a high computational demand, just from the fact that we're using AI and a lot of software. And there's also, like, once again, there's just limited generalizability because of the different areas that we're studying. But there are certain ways to overcome these limitations. One being local data collection, just using our own data here in the Central Valley, as well as training the AI to be specific to those crops and other industries. And I did hear about BioServe a bit while ago, being a project trying to start up an online portal that would contain a lot of data for our produce, biomass, and things that just go on for agriculture. And this would be a good hotspot of containing information and data that could be used for the life cycle assessments that would help lessen the overall damage that comes from large amounts of data, because it takes a lot of time, a lot of resources to do so. So overall, AI does show a great promise in helping facilitate life cycle assessments. They do show high accuracy and outperform traditional LCA methods. They are great at handling large data sets, especially when they're not linear. They're just helping out a lot. But I do want to reiterate the limitation that the studies are only applicable to those regions, and we must use our own data to conduct these studies. And having the help with BioServe and other projects, just making all of this data publicized, would help out a lot in conducting the LCA. I would also give a huge thanks to London Peachvine, Beam Circular, and my professor, Noe Hughes, for giving me this opportunity, and my partner for partially this time. Thank you.
Thank you all for being here, for coming. For those of you who stood through the whole presentation, that takes a lot of dedication. We really appreciate it. If you guys have any questions, our students will be here for another 15 minutes. By their posters, you're welcome to ask any questions. After that, for our students and faculty, we do have a reception at the MESA Center, so don't miss that. Georgia, do you have any announcements for? No? Okay, all right, thanks again, we appreciate it all.